Hello and welcome to this EE328 lecture video on time domain solutions of discrete time systems. In this lecture we are going to be addressing two of the special cases that you may come across that break the mold of the methods presented in the previous lecture. The first special case is when the characteristic polynomial has repeated roots, or another way to say that is repeated characteristic roots. So let's take, for example, the following discrete time system, which is an n equals 2 order system. And let's say, for example, we want to find the zero input response for the given initial conditions. Now, as a second order system, we need two initial conditions to fully specify the ZIR. So let's identify a couple of the coefficients. So here, a sub 0 is 1, a sub 1 is also 1, and a sub 2 is 1/4. And so identify those coefficients because we're going to start to skip the whole plugging in r to the n and deriving the polynomial that way. A shortcut is to just write this as a0 r to the 2 plus a1 r to the 1 plus a2 r to the 0 equals 0. So in this case that factors to r plus 1/2 quantity squared equals 0. So the two roots of this polynomial are both negative 1/2. So this is why it's a special case. We have a repeated root. And in this case, the homogeneous form of the solution is going to be some amount of that root raised to the n plus some other amount of n times that root raised to the n. Now, how much of C1 and C2 do we need? Well, that's where the initial conditions come in. So the zero input response at time -1, we are told, is equal to 0. And in our formula, that works out to be C1 times the characteristic root to the -1 minus, so here's the -1. This is, if you like, n equals to -1 times C2 times the root to the -1. Now this works out to be C1 minus C2 equals 0. So that's one equation but two unknowns. This is why we need the second initial condition. So at time n equals -2, we're told the system has output -10. So now we just plug in n equals -2 into our homogeneous form. So that's C1 times -1/2 to the -2 minus 2 times C2 times -1/2 to the -2, where again this is our n equals -2. Okay, so if you simplify this, you get something like 4 copies of C1 minus 8 copies of C2 has to be -10. And so now we have two equations and two unknowns which we can solve simultaneously via your favorite method. And for this particular case, we get actually C1 equals to C2 is 2.5. So this is not always going to be, repeated roots don't always give rise to equal residues, but in this particular case, they do happen to both equal to 2.5. So final answer is the ZIR as a function of n is 2.5 times the characteristic root to the n plus n times the characteristic root to the n. And all of this is valid for times greater than -2 technically, but we're really only interested in them in times greater than 0. The second special case that I want to address is when the forcing function, or the input, contains a characteristic mode. So I am going to take a familiar case here. This is a LTI system whose characteristic mode is -1/2, and I am going to excite it with an input that is -1/2 to the n. Right? So from before, we know that the homogeneous form of this solution is -1/2 constant times -1/2 to the n. And so because this matches with this, that lands us in this special case. And so for example, for this particular example, let's find the zero state response. So ignore initial conditions or set them to 0, and then solve for the output from time equals 0 onwards. Okay, so now that we know that we're in the special case number 2, and remember, how do you know that? Well, first you have to solve for the characteristic modes. So that's why, when you're doing those time domain analyses, it's often pretty beneficial to just find the characteristic roots, even if you are trying to find the forced response, because in this particular case, knowing the characteristic roots helps us choose the form of the forced mode. So we are going to choose a forced mode, or a forced response, that could possibly be some amount of the input as itself, and some other amount of n times that mode as well. Okay, so how much are k1 and k2? Well, we don't know until we plug this forced solution into the inhomogeneous Diffie Q. So this looks like y of n, so k1 times negative 1/2 to the n, plus k2 times n times negative 1/2 to the n, plus 1/2 of a delayed version of this. So k1 times negative 1/2 to the n minus 1, plus k2 times a delayed n times a negative 1/2 to a delayed n. And this we want to be equal to negative 1/2 to the n u of n. So if I pick, so for n greater than or equal to 1, then all of the steps involved here, all the step functions, have turned on. And so that means I really don't have to concern myself with them because they're all 1s. So for n greater than or equal to 1, I can rewrite this left side of the equation in a kind of a peculiar form, but I hope you see where I'm going with this in a bit. So k1, I'll just copy the first term, plus k2 n negative 1/2 to the n. And now what I'm going to do is I'm going to try and write the rest of the terms to look like these two. Right, so they've got a bunch of delays, n minus 1s in them, and my goal is to get rid of those delays. And I can do that in the following way. So I get the factor of 1/2, and I get the k1, and I want to write this as negative 1/2 to the n. Now, how do I change the exponent from n minus 1 to n? Well, I can divide by one of the bases. Then I'm going to take the 1/2 out in front, times k2, times n, times negative 1/2 to the n divided by the base, plus 1/2 times k2 times negative 1 times negative 1/2 to the n divided by the base. So let me make sure that everyone follows where each of these terms came from. So this one went straight down, this one went straight down, this one came from there, and the n I tracked there, and the negative 1 I tracked there. And so the idea is that on the left-hand side, I've got terms that all look like either negative 1/2 to the n times a constant, or negative 1/2 to the n times a constant. And so what I'm going to do is I'm going to try to hatch out in different directions here. This has no multiply by n, this has no multiply by n, but these two have a multiply by n. Okay. So what happens on the right-hand side? Well, we have negative 1/2 to the n, and if we're assuming n is bigger than 1, then the step has fired. A step is on, so we don't have to write it. And 0 n's times negative 1/2 to the n. And I'm calling attention to this because this term looks like the rightward slanting hash marks, and this term looks like the leftward slanting hash marks. So this is called matching coefficients. So for the terms with n to the 1 power, on the left-hand side I have k2 in this term, and I have, well, the 1/2 and the 1/2 will cancel, and the negative sign comes up, negative k2. And on the right-hand side, I have none. So, I mean, it's true, but it's not really helpful, right? So let's try the end of the zero terms. So from the first, I have k1 of them. And from the third, I have negative k1 of them. And from the fifth, I have k2 of them. So let's track that. This k1 came from here. This k1, this negative k1 came from here. And the 1/2 canceled the 1/2. The minus in the denominator canceled the minus in the numerator. And so then the plus k2 came from there. And on the right-hand side, I have one copy. Okay, so this tells me that k1 will cancel the k1, and so k2 has to be 1. And because this is called the particular solution in your math terms, I only need one such solution that satisfies the inhomogeneous diffie Q. So then I'm able to pick any k1 that satisfies this system, and the most convenient k1 to pick is k1 equal to 0. Okay, so in this case, we are now ready to solve for the ZSR. So y ZSR in the time domain is equal to the forced response, so that's 1 times n times negative 1/2 to the n, plus the homogeneous response, which is some amount of negative 1/2 to the n. Now, how much of that homogeneous response do we need? Well, at time equals negative 1, we need the zero state solution to be 0. And so I get 1 times negative 1 times negative 1/2 to the negative 1 plus some amount of negative 1/2 to the negative 1. This and this drop away, and I get C equal to positive 1. Okay, so then final answer in the time domain is negative 1/2 to the n times n plus 1, all of that in non-negative time. Great. Thanks for watching. I'll see you in class.